Um, so this is what we're going to cover today. We're going to do a brief introduction to Newcomp, where we came from and who we are. Then I'm going to talk about some interesting research, mostly just things that have kind of captured our attention and really got us excited. You know, this field is very dynamic and is evolving on an almost daily basis. And so, we're always reading and looking at new research and stuff to, you know, for new discoveries that'll be coming down the line. We're going to talk a little bit about our approach to some of these projects and how we structure them. Then look at an example project and kind of finish with some exciting tools and things that you can do to get started. So first, a bit about Newcomp Analytics. So Newcomp Analytics was founded in 1997 and has been a dedicated analytics practice since then. We've worked with banking, retail, telecom, large Canadian companies, U.S. companies as well, and done many different successful projects. We provide services and training, education. We actually were at Alberta Health Services as part of the IT division doing some machine learning training, and we also partner with a number of vendors like Alteryx or IBM, Tableau, DataRobot, to help implement those solutions and really just cover the whole stack of analytics. Chris actually, who runs the advanced analytics practice in Calgary, started out here a couple of years ago, and now we've kind of built it up to a small team in Calgary as well, but the majority of Newcomp is based out in Toronto, but our consultants kind of work nationwide and are ready to work on any kind of project. So in terms of what, we're a consulting company, and we help other companies. So we're not gonna, this isn't gonna be a sales kind of presentation, or we're not here to tell you like data is the new oil and do this rah 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 kind of speech. We're really trying just to keep everything grounded and practical and pragmatic, and talk about kind of how we've approached AI. So I guess I'll just introduce myself as well. So my name is Tom Krawitsky. I was born in Calgary and went to the U of A for a computing science degree. I originally started in software engineering, so more about code and building large-scale software systems. But then as I got through my degree, I kind of started to get more interested in AI. The University of Alberta actually has a really decent AI research department, and so reinforcement learning, if you've ever heard of that, was kind of the original paper was one of my professors wrote it at U of A. So at the time I was just swamped, right, and trying to get through it all. I took a course on machine learning and we covered all of neural networks in a week, and it was 100 slides of math, and I was like, oh man. But now since then, DeepMind actually of Google has opened an office at the U of A, and it's a pretty good research hub. Canada's actually pretty well known for its AI research. So anyways, that's where I came from. And then I got into Newcomp and became more of the advanced analytics consultant, so doing more of the predictive modeling and AI and ML. And as that practice has grown, it's come to take up more and more of my day. So that's a little background on us and where we're going, but definitely lots of exciting times ahead. So this talk is not going to be like a super technical deep dive. That if you want to do that, there's some really great research papers to read. It's also not going to be kind of too high level or fluffy. It's just about our approach. So first, we kind of want to define what we mean by AI. If you've just been reading the news or on the internet in general, you've probably seen a ton of articles like this. AI technology could disrupt half of jobs, or something kind of more silly like Adobe adds AI-powered zoom and enhance to Lightroom. Is that AI? But there's big questions out there, like will the rise of automation and AI threaten job security, or what's Uber doing as they resume self-driving testing after an accident? And even the bottom right article, which is probably relevant to you, like artificial intelligence used to detect ovarian cancer. So this is in the media, and there's a lot of hype and buzz going on. And so as someone who may not have as much of may not be, as deep in the community, it can be sometimes hard to know what is real, how do we actually get started with this? What research is actually going on? So we're, we're trying to keep a very practical approach to all of this. So specifically, at Newcomp, when we're talking about AI, we are talking about applied machine learning. So, we're not necessarily talking about like crazy advanced reinforcement learning, or even kind of some of the more sci-fi projections in the future, or even like kind of robotic process automation. For the most part, we're talking about predictive modeling and applied machine learning. So predictive modeling has been around for a long time, right? Things like linear regression or logistic regression, or even neural networks. I believe that neural networks actually were first developed in the 50s and 60s. The idea that you could take a input feature and activate it and have it kind of model a non-linear relationship between the inputs and outputs. But it's only really in the last, I don't know, maybe 5 to 10 years that we've really seen that technology really come into its own, largely because of two things. First, large data sets. It's kind of amazing. We went from in 2007, like almost, no one had a smartphone. The iPhone debuted in 2007. Everyone just had those feature phones, to now where like effectively everyone has one, and these devices are constantly generating data. And the amount of data in the world grows at an astounding rate. So modern machine learning algorithms, especially the kind of deep learning algorithms, require huge amounts of training data to get to the accuracies and to do the amazing things that they can do. And so the rise of all of this big data has really enabled this. And the second part is abundance of computing power. So, in the 1950s and 60s, just getting a small network to run or a linear regression required a fair amount of computing power. But now, like, you can go on to Google Cloud or Amazon or IBM and get like essentially a supercomputer for like dollars an hour. Like at Newcomp, we've regularly gone onto a cloud provider and spun up like a 32-core server with a ton of RAM, and then Google's making these TPUs that you can use. So the ability to just have huge amounts of data and lots of compute has really helped push the technology along, which is why companies like Facebook and Google and Amazon are the ones kind of leading the pack in terms of deploying these technologies, because they're the ones with the most compute and the data. So one of the cool side effects of all this, compute and data and intense interest that there has been, like some might call it hype, but I think, it might be legitimately deserved, is that people are getting really interested in AI machine learning. So I don't know if any of you have heard of the NeurIPS conference, which is the Neural Information Processing Society. It's a conference on machine learning where kind of the best and brightest go to publish their papers. And, it used to be pretty niche, like a couple hundred people would go, and, this is in like 2005, and you'd publish a paper. And I read last year for NeurIPS 2018, it sold out in like 4 minutes, like 10,000 people or something, or 5,000 people, and it sold out like almost immediately. And then the quality of papers is just astounding. And so there's kind of been this snowball effect where people see, others doing really cool things. They have access to better data and access to lots of compute, and this kind of all snowballs into a pretty exciting space to follow. So I thought for today's talk that we would just talk. Awesome.
Yep.
Okay. So continuing on, I wanted to talk just about two really cool research papers that we found. One of them is in the area of natural language processing, and the other one is in the area of computer vision. So I'll just talk about those. So for those who don't know, maybe natural language processing is the ability for a computer to understand natural human language. So, in the past, when you're interacting with a computer, you have to give really rigid commands. But if any of you have used things like Google, like Siri or things like that, the idea is that you can communicate with them in very natural ways. And also, language modeling is kind of an area of research as well, and that's kind of understanding the structure and context of language, right? So when people talk to each other, there's a ton of implicit knowledge that we all carry around, right? And that's why making, understanding from a computer is really hard, and generating realistic text is really hard. And so in these three areas, like translation, speech recognition, and speech synthesis, there's actually been some pretty nice breakthroughs in the last couple of years. I don't know if you remember like Dragon, Naturally Speaking, or any of those like built-in Windows speech transcription software from the past, but they weren't very good. And now, with these new technologies, they're pretty amazing. So this first paper I wanted to talk about actually came out just last Thursday, so it's pretty new. But it was one of those things where you read it and you were just like, wow, like I cannot believe a computer was able to do that. So I had to just include it in here. I was going to just share my screen and show the website, but I think it'll be easier just to keep it on the slide deck for now. So this paper is all about language modeling. So it was published by OpenAI in San Francisco, and you can go to, if you just search for OpenAI, you'll see it. They have this beautiful website where they walk through the paper and everything like that. But so I guess the key idea is that most language models we have operate in a very like strictly supervised sense. So in machine learning we talk a lot about supervised and unsupervised learning. With supervised being we have the input data, and we want to try and find a mapping between that and the output data. So, like with vision, it might be tell if this is a picture of a cat or a dog, or it might be tell if this example of a credit file indicates, they're risky or not risky, but we already know the input and the output. And so with most natural language models, they will use this very structured supervised format. So for example, translation to English to French. The way that these models work is you take a sequence of input words, maybe in English, and then you have the sequence you want. So a human translator has done that. And the model learns the association between all of these English translations and all these French translations. Things like question and answering systems, where you might ask your phone the answer to a question, or Google or something like that. They use a similar sort of system, only the input is a question and the output is the answer. And so there's a number of different kind of language modeling tasks that all attempt to solve a different problem, translation, question answering, etc. But the state-of-the-art ones are like always trained in those very, very narrow domains. So what made this paper different, the Better Language Models paper, was that they took an unsupervised approach. So they weren't training the network to solve any key task. All that it was meant to do is, given like a series of previous words or sentences, all it was trying to do is kind of predict the next thing that you would say. So the next word or the next sentence. So it's taking this input sequence and trying to predict the next one. And critically what they did is they scaled it up to an enormous scale. Like they got a new data set. So they went on Reddit and they scraped all of the outgoing links from Reddit. And so they had this giant 40 gigabyte data set of all of this text, just tons of people, communicating, writing articles, all these things. And they just let loose this model using some fairly substantial processing power that they had access to from Google. And so the model was huge. Like it had 1.5 billion parameters, which if you know anything about like neural networks is astounding. But they found that if you condition the network the right way, it actually was able to achieve like state-of-the-art results on like 7 of those 8 natural language tasks. So it was as good or better than all of those expert systems without actually being trained to do them at all, which indicates like a pretty good degree of generalizability. And like on their website, they have some really amazing examples, but the coolest example I saw is like you can prime the network with the start of a news article or the start of a story, and it'll actually just keep generating text and actually fill in the entire story. So, on their website, for example, they prompted it with like, in a shocking finding, the scientists discovered this herd of unicorns living in a new valley, and it actually wrote like, this doctor, an evolutionary biologist, visited the Andes Mountains and found this new valley where no one had been before. And I encourage you to go read it. Like, you can't tell that it wasn't written by a person. And it was just like really cool. Another thing that was really amazing is if you write like a long series of text, like maybe a news article, you can get the network to create a succinct summary of it just by priming it with a certain phrase. And so the network will actually take all of the context and compress it down to a single paragraph. And it does all of these things with one network. They're not, separately trained or anything like that. So just it's a really good indicator of like generalizability, that the model isn't just memorizing what it's seen in the past, but it's actually got some genuine understanding there. So it's really cool. I think there could be many interesting applications, if you could get a system that just understands how to answer questions and is good enough, like it could almost do anything, right? You could use it for a search or for filling in, like writing news articles or something like that. So I think, there's a lot of potential there. The authors, they kind of realized that the ability to take a prompt and generate realistic text that looks exactly like it was written from a human could be risky, right? And so the way they figured this out is they actually put in a prompt that said like recycling is bad for the earth. And they kind of started an argument, and the system actually wrote like a pretty compelling essay on why like recycling is a bad idea. And they were like, uh-oh, like, what if, in an era kind of fake news and things like that, being able to generate, infinite, very realistic stories is risky. So they include a really nice section in the paper about the implications of this research and they've decided to release the model kind of in a controlled way, a much smaller model, so that it doesn't have potential for abuse. But these issues, things like AI bias and abuse like that are definitely things that are being discussed more in the community. So I think that'll be really important in the future. So we're trying to keep that in mind when we're dealing with machine learning systems that are making real decisions, right? For real people, that these systems don't operate in a vacuum, right? And they can have some pretty massive implications. So the second paper I wanted to discuss is in the domain of vision, and that's really where a lot of the exciting gains have been made, especially since 2012. People started using convolutional neural networks and really deep neural networks. So some of the places that this is used is in like crop monitoring. So for example, in a lot of developing countries, farmers they have new crops, but they might not have, as much skill with those newer crops, like trying to figure out exactly how they're doing. And so researchers have developed applications that you can take a picture with your camera phone of the leaf of a plant, and it can identify like common causes of why it might be sick. If it can identify parasites or fungus or something like that, or using too much pesticides for all these different crops. And so it's not, just the developing world. Like anywhere here, you can fly over a field and use deep learning software to figure out the health of your crop. So that's really cool as well. Second one you've no doubt heard about is autonomous driving. I'm sure everyone's seen the Tesla videos. Those are really cool. Tesla's actually probably one of the more advanced ones, but a lot of cars now, even cheaper, more affordable cars, have systems like lane keeping assist and smart following. My dad's new car, like he's got a Honda Civic, and it identifies speed and traffic signs and will like show them on your heads-up display for you. And all of these are being driven by advances in deep learning. And the last one is diagnostic imaging, which is what the next paper I'm going to talk is about. So I might as well just get right into that. So this paper is really interesting as well. It came out in October of 2018 and was again one that I found just very practical and very interesting. I really do need to show the actual pictures from the website, so I might just try and do the screen share so you understand, but I'll just give the background first. So this just my overview. So this is from a series of American hospitals, but the paper was designed to kind of handle the task of fractures. So like, fractures in your wrists or in your arms. And so like when someone visits an emergency department, oftentimes a fracture is a really common person to visit, just general trauma. And so typically they'll get an X-ray, and that's the common diagnostic method. And then either, a clinician in the emergency department will diagnose it, or if it's too complex, they'll try and send it to some sort of specialist. But oftentimes, especially in emergency departments that are really crowded and really quite frantic, there often isn't the time to kind of get a better second opinion on diagnosing these fractures. And this can have some pretty like serious negative implications if you miss it early. So the researchers were looking for an area where like there's kind of misdiagnoses are fairly high. That's in an imaging domain. So there's been kind of a lot of talk about applying AI to healthcare. You see all these articles, but what they were trying to do is be very practical about it. A lot of these systems, people make these grand claims, and they end up being a little more brittle than you thought, right? They don't have the vast like breadth of experience that any MD or nurse would have, and so often these systems are missing that greater context. So the authors tried to keep it fairly constrained to a limited domain. So what they tried to do is they didn't try to replace anyone, but what they did is try to take the expert knowledge of like an orthopedic specialist or a radiologist and say, can we take their expert knowledge and use it to lift the level of accuracy of like just an ER physician, right? Or even like an RN or something like that, that's operating, in an ER and isn't designed to just work on that very specialized orthopedic kind of situation. So what they did is they actually got, I think it was around 30 orthopedic experts on arms and hands to annotate a bunch of different radiographs, and they'd actually used radiographs that they had integrated in the past. So they essentially took these images and they marked, where a suspected fracture was in the image, and then said like, yes, this contains a fracture, or no, it doesn't. And then what they did is they trained a convolutional neural network that was something called a segmentation network. So what it's designed to do is take an image and it kind of creates a compressed representation of the information in that image. And then it kind of scales it back up and also segments the image into areas that contain fractures and areas that don't contain fractures. So I wish I could share the images from the website, but essentially you have screenshots of a patient's arm with an X-ray, and you kind of have this yellow band, like almost like a heat map over the area where the network suspects there could be some sort of damage or some sort of fracture.
Hey Tom, can you explain how basically a neural network can actually take a photo and the fact that and basically photos are in fact data, and explain kind of the RGB?
Oh yeah, totally.
Yeah, just maybe at a quick, yeah.
Yeah, so I mean, when you have an image, all that an image is a series of pixel values, right? So typically we use something like RGB. And so if you have an image that's like maybe 1,000 pixels across by 1,000 pixels down, each one of those million pixels will be just three numbers. It'll be the amount of red in the image, the amount of green in the image, and the amount of blue in the image. And so by varying the concentrations of red, green, and blue, you can make an image. But if you look at an image in its raw format, like it doesn't look anything like you or I would understand, right? It's a bunch of like numbers from 0 to 255, and it's actually really hard to make any sense of it, right? And so a computer doesn't have millions of years of evolution to think about these kinds of things. Effectively, it's just seeing these raw numbers like 50, 70, 30, and it's like, okay. So what these neural networks do is they take that raw image data and they feed it through a series of transformations. And what specifically convolutional neural networks do is they try to look at sort of groups and clusters and patterns in the image and then create higher level representations of them. So I think it was Google published a really interesting paper on this where they took a neural network and they tried to get it to predict different pictures of animals like cats and dogs. And they have all these different layers. So the first layer takes the raw input data. The second one kind of transforms it. It applies a multiplication to it and activates it to this function. And essentially what it's doing is kind of like a brain. It has these activations and information flows across the network, and it kind of learns to associate certain patterns in the input with the desired output that you want, right? So what this network did effectively was it tries to find like higher level features. So if you're talking about the dog or cat example, that would be like the lower layers kind of find shapes, or they might find lines, and then the more intermediate layers kind of find things like edges, so corners or circles, and then the higher level ones will start finding things like faces or things like um, eyes or things like that. And then the final one, if these features are present, it will make a decision. It'll say, yes, this is a cat or this is a dog. And so this paper is kind of an example of that. So Jesse, do you think I can just share? I'm just going to try and share my screen, just my desktop.
Yeah, give it a whirl. And worst case scenario, I guess we could just move it to the top left, eh?
Like, can you see this?
No. Wait a second. It's loading. Yeah, there you go. We can see that.
Yeah. So effectively, this is kind of what they had, the original radiograph, and then what the network does is it takes those images and puts it through something called a UNet. So it kind of, each of these layers makes like a more compressed representation of that image. And then they kind of create this heat map of where the network suspects a fracture is. And then they kind of upsample it the other way and apply it back on the original image. So you kind of get the original image with this overlay saying this is where we suspect a fracture is. And you also get like a probability, based on all these things. And so the paper is really interesting to read, but I'll go back to the slides now.
Sure. And Tom, Catherine had a quick question. Do you have a more detailed, but still for dummies information about the computation of this image classification graph? She said there's in brackets, sorry, coming from TensorFlow and also a beginner.
Oh, well, we could,
URL
I could send something over.
Sure.
You mean about the paper or about just
I'm not sure.
in general?
Yeah. Whatever you have.
Okay, yeah, no, definitely at the end we can send something over for sure.
Sure.
But anyway, so what they did is they had this network and they found that it was able to get a pretty high degree of accuracy, but they wanted to test it in a real world situation, right? So what they did is they ran kind of a controlled experiment where they took a series of new fractures that the network hadn't seen, and they kind of randomly assigned them to different emergency medicine physicians and saw if the presence, like having the computer assist them, would help them or not. And so, one of the issues that I've kind of seen with medical imaging in the past is that they really increased or they decrease the specificity of your testing without increasing the sensitivity. So essentially that means you're getting more false positives. Like the previous computer imaging ones would go like, there's probably a tumor here. And now, of course, as the physician, you've got to follow up with that. And so it tended to result in kind of more overdiagnoses and then probably a lot of unneeded testing and things like that. So with this, they actually found that just kind of seeing that suggestion of the fracture increased both the sensitivity and the specificity. So they found that the relative reduction in that misinterpretation rate was about 47%, which is a pretty big deal. Fairly encouraging. So it was able to help the more general kind of emergency physicians and give them some of the knowledge of the very specialized, orthopedic experts who wouldn't always be available, right? So it was able to effectively just augment their abilities. So that's very encouraging, right? And so another important thing to mention is that for the examples that were really quite difficult, they actually measured it as a function of time, like accuracy is a function of how long it took you to come to a decision. And normally as the image gets more and more ambiguous and tricky to identify, the amount of time it takes and also the accuracy, will drop. And so they found that with this network, the rate at which the time kind of fell off was quite reduced as well. So, it would take them way less time to come to a final judgment. So it kind of helped a little bit with speed and also with accuracy. So this isn't a complete product, right? It isn't something that you can buy and plug in. But I think the thing I took away was that the model of taking an expert's knowledge and trying to kind of apply it to someone who maybe for the time or their degree of specialization just doesn't have time to go into it. I think that those could be really good use cases. And some of the example that we'll talk about at the end that we kind of did is kind of similar to that as well. So obviously there's some limitations to this paper, right? It was only done on wrists. The domain is very narrow. It was only testing if a fracture is present, but it wasn't talking about the full spectrum of treatment. So there's a lot more kind of that has to be ironed out, but I just think it was really notable for me. So if you wanted to, the paper is pretty good. It's on hosted online on PNAS, so you can go and find it there. But yeah, that was a really interesting one. So I'm sure there'll be lots of discussion about that. Moving along here, I just wanted to talk now about our approach, like what we've learned, as machine learning and practitioners getting started up here in Calgary. So at Newcomp, we're always kind of thinking about the analytics value curve. Like we're not Google or we're not Tesla. We're not trying to solve some grand challenge like curing disease or making cars drive themselves. What we're really trying to do here is move people up this analytics value curve. So when you start off, you've just got data, then you try to store it somewhere, you try to organize it, do basic reporting, then do dynamic reporting. So you can ask questions. You might get into statistical analysis. Then you start training predictive models, trying to figure out based on the past, like what will we think happen? And then you kind of move into prescriptive models. So given what we think will happen, what should we do? And at the end, you kind of get into the full like process automation, like this is automated, it kind of takes care of itself. And so we want to try and just wherever people are on this curve, lift them up. And so to that end, we've kind of come up with this internal process for how we think about machine learning. And this is, evolving over time as the field develops. But our basic steps are, first, you've got to think about a general problem that's a general pain point. So this could be a business problem, or maybe something's taking too long, or it's costing too much money. And then you want to really refine that into a more specific problem, So say, for example, maybe you have an email system and you need to kind of monitor communications and make sure that people aren't disclosing company secrets or something, or patient information, right? So you'd say, the problem is we're disclosing patient information. Maybe the specific problem is people are disclosing this in emails. Then you'll want to go into your machine learning use case. So in this case, the machine learning use case could be, given the text in an email, can we classify it as either, a violation or a safe email? From there, you'll have to identify what kind of data you have, right? Oftentimes you see companies that have like a lot of cool data, but they don't really know how it's structured or why they want to use it. So we find like having the use case first and then trying to see the quality of your data is important, because you can always generate more or maybe think about a better way of storing in the future that will lend itself to this kind of analysis. So in this case, you might have a database of emails flagged with ones that are objectionable and ones that are not. And then fifth is where you actually get into the real modeling. And so there's a lot of options. You could do something like this in the cloud. You could have a company design a system for you, or you could write it open source. I know someone on the call had mentioned using TensorFlow. There's all kinds of really great open source libraries. And then sixth, you'll be iterating. Like machine learning isn't something you just buy and kind of drop in place. It's something that you'll want to take a lot of small iterative steps. But once you start moving in the right direction, we find that iterating yields some pretty cool results. So now I'll just talk about one of our projects and kind of walk through these steps and talk about how we developed it. So this was an example from a finance company, a local company based in Calgary here, and it's still under active development, so we can't go into very, very specific details, but we'll try to give a general overview. So this was a banking client. They have a ton of like transactional data, so very low level data that their clients give to them. And what they're trying to do is they have these analysts who perform both credit risk and also financial health assessments on their clients. So like, for example, when you go talk to your financial advisor, they might say like, this loan payment might be too much for you to support, or we might need to, restructure and combine these together or something like that. Their problem is that given the amount of data they have and that they're a relatively small company, the current process just takes a long time, right? If you have to just like look through raw transaction data and figure out, what this is and how they're spending it, it can just take a long time, right? So what we came in to do was kind of audit their existing system and then try to apply machine learning to improve the process. So in two key areas. The first one was transaction classification. So like banking information, people come in and then you need to categorize these transactions into certain groupings. So, if I see a transaction come in and I know that this much is going to a mortgage and this much is going to a car payment, maybe there's some way that we can reduce one of those and kind of improve your financial health. But when the transactions come in, these people are kind of from all over and from all different walks of life, and typically the institutions they're from aren't consistent in their naming, and so you have sometimes it's very unclear as to what they are. And then second, given that information, once we kind of know what all this financial information is, can we kind of make recommendations or give kind of a suggestion to their financial health? So to that degree, we had a bunch of this data from the past that we generated a bunch of indicators about. And then we had what their prior analysts had recommended, right? So they said, oh, this person, they're probably going to be too high on this like certain debt ratio, and they probably won't be able to make a payment. So we recommend this course of action to help them out. So I wanted to see if we could develop a system that would automatically kind of volunteer these for new applicants that came in, so the analysts would have to spend less time. So just an example of the transaction classification. This is part 3. Like, this is the machine learning use case. So we had a description, and then we would want to assign it to a category. So like, the first one, Tim Hortons, is fast food, TELUS is mobile, telecom, Netflix is a subscription. And that way you can kind of see and get a better sense of where your money is going every month, for example. But what we found is like the data would be kind of more like this when we looked at their real data. So you'd have, mobile bill pay, TELUS TV, or like payment deposits, int, and a lot of the problem is like they tried a simple rule-based system where they said like, okay, like Tim Hortons, this is fast food, but then something would come in that was Tim Hortons, but it was completely different. Or you might have Netflix with a reference number, and your paychecks also come in with this kind of reference number. And so using a pure rule-based system just like didn't scale, and they'd find that their analysts were taking a long time just trying to figure out what all these things were. So we wanted to use a machine learning system that could understand like, oh, if this says pay, it understands that in this case it means payroll, but in this case it means that you're making a payment, or that it's a return or something like that. So we started out with some simple models and have basically just been refining them over the last 6 months. But effectively what we have now is, yes, we're using TensorFlow. We take our input and output pairs and we encode them into sequences. So we kind of pad them so that they're all the same length. We do some pre-processing, so like kind of stop words or like very commonly occurring words that don't have a lot of discriminative ability. We remove those as well.
Can you explain a stop word?
Yeah, so in natural language processing, a stop word would be a word that's used quite often, but isn't, very specific. Something like the, an and, or, like if you take a book and you summarize the most common words, you'll usually find that the, an or, an and are things that appear very often, right? So we
ignore them basically.
Yeah, effectively remove them because they're present in every transaction, and so they don't really add too much ability there. So we're trying to kind of reduce the data to something a bit more specific. Then it might be too specific for this talk, but we take these sequences and we actually feed them into something called a recurrent neural network, which is designed to make predictions based on sequences of data. So the machine translation example I talked about, and even the speech recognition, they all operate on sequence data like that. And so basically at the end you have output probabilities of what each category is. And so we deployed that system. It's written in TensorFlow, hosted with TensorFlow serving, and then deployed actually in a kind of elastic Docker-based container system. If you want to go more into that, we could talk into it. That's more of an infrastructure discussion, but this is the model we ended up deciding on. But we started off pretty simply, with just like looking for the presence of simple words, and then we kind of moved more into the sequence models, and just a very kind of slow, measured, iterative approach. And so essentially, right now, what we've been able to do is reduce the time by at least 50%, because I no longer have to look through all of this data. There's a lot still going on. They're in active consultation with these clients. But we've also the accuracy on our kind of holdout set, that we just a completely separate data set. So we leave some of it aside, and the machine has never seen it before, is actually fairly high. So that one's actually going really well. And then that one's in active development, so we're continuing to refine it. But it's been a really kind of fun project, and we've had a lot of ability to try out new things as we kind of move forward with this client. So I won't go into the step 2, just in the interest of time, which is kind of the recommendations. But it's a very similar thing. Like, given this sort of data, can we recommend a course of action or something like that? So I see we're kind of approaching the top of the hour. I'll just briefly talk about some of these tools, and I really want to make sure I get to the next steps point to leave you with something to try today. So just in full disclosure, these companies, we are partners with the ones that I've put in here, but they don't necessarily know we're giving this talk. I included them just because they represent kind of the big areas of how you get started with machine learning, and we just wanted to include them because there's something that we use in our day-to-day workflow. So one many of you are probably familiar with is Alteryx. Just helps with the pre-processing and blending side, and also validation of early models. So you can connect to any sort of data source. It's all drag and drop. I know you at AHS actually do use Alteryx, so but it's just a really great way to kind of prove out your ideas and get all your data ready without having to mess too much with Python or pandas or scripting languages or something like that. And you can also train logistic regression and smaller neural networks and stuff directly in Alteryx. So definitely very fun software to play around with if you if you can access it. Yeah. This next one is probably the most exciting thing that I'm interested in right now at Newcomp. It's a new partnership that we have with a company called DataRobot, and what they're trying to do is automated machine learning. So we talked about all these steps, like getting your data and then like doing the modeling and testing it and validating it. And what DataRobot does is actually uses the best practices of data scientists to train hundreds of models simultaneously and then deploys them kind of in one step. And so you get this really fast kind of seamless model deployment solution. And so you can just essentially put your data in and it'll generate the features for you, train the best model, make sure that it's actually predicting what you want, that it's generalizing correctly. And so that's just a really cool tool, and we're really excited to kind of get into more of those projects. Really cool. Then there's also the cloud. So we have had a number of projects that use cloud-based machine learning APIs, and there's ones from, we're partnered with IBM, but there's all the major vendors will have these, and these are really cool because they take, again, their best practices for their models and allow anyone to use it. So, there's like IBM has a natural language understanding API where you can send a snippet of text and it will give you some insights into it. It'll tell you all the different verbs and the entities and components that it's found. You can also train a classifier, so you can say, like, just put in a CSV of here's some input text, and this is what I want the output to be, and it will automatically train that for you. They also have like text to speech and speech to text, as well as translation services, and they're all accessible via really cheap API endpoints, where you're paying a couple pennies or something for every 1,000 requests. So definitely designed to operate at scale. So I know a lot of times you're dealing with confidential information, but if you have the ability to use a Canadian data center and you can make sure those concerns are met. Sometimes the cloud option is really exciting, and we found that that's a really easy way to get like a cheap and quick deployment out the door. So those are really exciting. And then last, just open source. This is kind of where, all these papers are implemented using open source technologies. The community is great. People are always trying to share. So, if you look online, you could use something like TensorFlow or scikit-learn or PyTorch or Keras or any of these to start training models right away. Use a Jupyter Notebook environment, and it's all open source and documented. So, you need a bit more skill as a software developer, but if you are confident enough and you can go in that direction, there's never been a better time to get into open source machine learning. So something like TensorFlow or Keras. So just wrapping up here, this is kind of the process. So I want to leave you with this: be thinking of a general problem, right? A pain point in your daily job. Try to think of specifically what is the key issue that we're facing here, and then try to see, based on text or vision or any of the other areas, maybe it's just simple predictive modeling, time series forecasting. Can we make this a specific ML use case? Keep your data sets in mind, choose a framework, and just kind of go for it and iterate, right? In terms of resources, these, I'm basically reading all the time. There's so much cool stuff going on. So I follow a number of data science blogs and news, one called Towards Data Science. I believe it's hosted on Medium. I found it just really useful. They have a really great diversity of stuff. People will post articles about training, capsule networks, crazy next generation type of machine learning projects. And then also, training my first linear regression. And so as I was starting out with modeling and things like that, I found, those blogs and kind of forums to be just a really interesting place. And the community is great. They share all the time. If you're looking for kind of more just general algorithmic and machine learning type stories, I like MIT Tech Review. These are just the ones that I personally have found useful because they have a weekly newsletter about what's going on in AI, and they try to keep a pretty balanced perspective. They're not just feeding into the hype machine, but they're also not too pessimistic. So I really like that. And then also a lot of vendors who sell or release these open source tools will have webinars. So, I know Google has had them, DataRobot has them, and then those are really great ways just to kind of learn how those companies are thinking about this problem. Second, if you are, you're kind of in and you want to learn, there's Kaggle competitions. So those are really fun. I'm sure a lot of you have heard of those, but it's someone will put up a public data set and they'll give you a challenge. So it might be predict the number of people who are going to use a bike sharing service, or try to identify whether this loan will go bad, or try to group these fragments of text together. And then people will compete and release kind of a live guide in code how they actually did it. And so if you want to learn, it's just a great resource. And then lastly, local events. So things like AI meetups. Calgary actually has an AI meetup. I know Jesse had talked about it earlier. I've been to almost all of those. I actually came in on the second one. It's only been going for about a year, but that's just exploded. When I first went, there was about 20 people, and now regularly you'd see a couple hundred, and there's thousands of members in the group. So that's really cool. And then corporate newsletters are really great. They'll just put out, what people are working on. And then also local resources like us. We're trying to kind of build and foster a community, an advanced analytics community in Calgary and abroad as well. So if you ever have any, cool machine learning use cases or saw a cool paper, we'd love to hear about it. And then if you want to go, more into a real project, we can help leverage our experience, that we've had from lots of clients to make sure that your project is staying on track. But, we're always looking to learn and try out new things and kind of move forward together. So, if you ever want to reach out, don't hesitate to go to our website or email me directly. There's all kinds of cool stuff happening for sure. So thank you very much. I hope this was informative and, it wasn't too high level or too low level, but, it's an exciting space, and I really just appreciate getting the chance to talk to you all about it and talk about what we have going on here. If you ever want to, say hello, we're right here in Calgary and Kensington, so by all means, thank you.
Thanks, Tom. Very much. We did record the session, so I'll have that posted on our SharePoint site here shortly. We did have a question whether you often remove punctuation when you're actually cleaning your data sets. I know that characters are typically set to lowercase, if I remember correctly, but punctuation was the question.
Yeah, so we experimented with a lot of different methods. We have kind of the raw data and then also the clean data.
Mhm.
For like our data, a lot of these examples are made for words and sentences where things like punctuation would probably be more informative. But because ours is kind of a lower level, like almost machine generated data, we found that just keeping kind of the raw text description and numbers are important, but like special characters are usually just noise. So this is something kind of an active area that we're kind of looking at, but for our specific use case, we just keep alphanumeric essentially. Any other questions?
Yeah, there was another one from Kayan. What method did you use to vectorize your raw data in the NPL project? Which I think was
So
yeah,
yeah,
NLP. Yeah.
so initially what we had tried was the kind of bag of words approach. So what you essentially do is let's say you had 1,000 distinct different words that were present. So like Tim and Hortons and stuff.
Mhm.
You would make a big long vector, and it would be zeros except for one place, with each spot in that vector corresponding to that word being present or not present. But what we found is that because our data, you can't really break apart the data into distinct words because they're kind of, again, they're machine generated and they tend to be very noisy. We
Mhm.
ended up doing it on a character level. So we actually take our alphanumeric characters and we represent those as a vector. So I think it's like a 38 dimensional vector. Same thing, kind of one hot encoded, and then we take each of those vectors as a character sequence, and that becomes the raw input to our neural network. So it's like a character sequence, and that seemed actually to work a lot better because it was able to extract, that these sequences of characters indicate kind of this concept like payment or payroll, whatever. So that's how we've done it so far.
There were, yeah, he was asking, the follow-up is, I mean, count, vectorizer, ngram, or TF-IDF.
So we originally used the count vectorizer. We didn't use TF-IDF because they were fairly short, and we didn't having sort of the inverse document frequency wasn't. We didn't find it super informative for us, and then we kind of moved into the character-based model, so we weren't actually using that for word mapping. But good question. I mean, that was kind of where we started, so. Any of those would be good. I know Keras has a built-in vectorizer for you that does a pretty good job, and I think that the TDF built into scikit-learn is pretty accessible as well.
That's great. Well, we're over time here, so want to thank everyone for calling in, and thanks so much, Tom.
Yeah, thank you.
Yeah.
Thanks everyone
Thanks
for
much.
attending.